kind of showing us a pretty balanced tree, right? So the left side and right side, they both have pretty much the same height. And so this way, it's really number of comparison that we have to do to adding an element or even searching for an element is really going to be maximum the height of this tree, right? So here, if I have 1, 2, 3, 4, 5, 6, 7 elements, or 7, 8, 9, 8 elements in this tree, and I'm trying to add the next one, the 59, maximum number of comparison that I have to do is 1, 2, 3. So that's the height of this tree. So maximum number of comparison is going to be maximum the height of the tree. So instead of n elements, we're only going to do h element, and h is going to be the height of the tree. I did some analysis before when we're talking about the sorting algorithm, such as merge and also even the quick, and I show you this tree structure, and I showed you that if I go for one branch, it's kind of like dividing the problem smaller piece, and then when we go to one branch, we really need to do each time work, right? So one branch, and that was a log n, right? So one branch or one height of the tree is equal to log n, and we really need to do each time, right? Log n time. That's the same concept. So the proof is they're going to be exactly similar. That why this is only log n and not anything else. So why h is equal to log n is the similar proof that I did to show you the performance of the heap and the merge sort and quick sort. So please review that again. So in the best scenario, if the tree is really balanced and in the left side and right side we have the same height, then we're going to have a very good performance as far as like number of comparisons. It's really going to reduce the the search that we knew, like linear search or binary search, to really be log n, which is going to be really fast, right? But we just have maintaining these numbers. The problem is happening when the list, when we're adding element to the binary search tree. As we add, if they were already in a particular order, even reverse order or natural order, then we're not really going to have a balanced tree, as you can imagine. Our tree become a different height. One maybe like one left in the left side, maybe you have a height of 1, 2, 3, or the other height is going to, or even 0, and then the other one, another part is going to be like more. And so since it's not balanced, right, h is getting very close to the number of elements, right? So h is become become like linear and very close to n. And n is number of elements. So if the height of this tree is getting very close to the number of elements, which is n, then it's not going to perform as order of log n anymore, and it's going to perform as order of n. So it's become like a linked list, really, right? So I basically only have left children, like left. So it's kind of like I have only next, right? So it's going to become like a very linear or flat data structure. So it's no longer looking like a hierarchical, nonlinear tree structure anymore. So that's why the binary search tree is really, it depends on what kind of inputs you have. So you can imagine if you're having, when you already know the average element, the value of the average element in your list that you're trying to add them to the binary search tree, then you can get a really good balanced tree. But if there's, again, the list is already sorted, and you keep adding them, it's not going to create a balanced tree. So I'm going to show you some animation here, and And for that, I'm going to use let me see if I can find it. Again, the book, the simulators are available in the book website. I know I put it somewhere close here so we can. Oh, right here. Let me stop this share and then share that animation. So hopefully you can see that. I have to make sure always that I am showing the same exact thing on and sharing exactly, you know, whatever I share is really, you can see the same thing. Otherwise I can mess it up. But like what we did, I don't know what was the issue really in the previous. It's kind of stuck in one page. So anyway, so here we have our binary search tree. Where is it? Oh, right here. I could see it. So we have our binary search tree animation. So I'm going to keep adding elements. I'm going to use the same element that we have here. I'm just going to add them into this list randomly. So I'm first adding 60. So I'm going to it's going to create 16, and I added 55. And I'm adding 100. Then 45. Then 57. Then I'm going to add 967. And then I'm going to add, for you guys in the see this page. Yes. And then I'm going to add 107. So this is going to be exactly like what we had in the example, right? So if I want to add 101 as we did, we know it's going to keep going all the way to get to the 107, and it's going to add it to the left side of the 107. And if I add the 59, it's going now this way and then this way, and then it's going to add it in the right side of the 59. So we added 59, so it's going to go in the right side of the 57. So now imagine I keep adding more element into this list. And so now, for example, I'm adding 10, 20, 15, 20, 25, 30. They're not showing it anymore. 35. I'm gonna see if I can maybe. Okay, it's not. So, okay, it's not a good example because it didn't show it for some reason. But as you can assume, it's all going to go light here, right? So because they're all going to be in this branch. So I have to, you have to do a new one, so don't worry about it. So I'm going to refresh this. So we're going to start from scratch. So imagine I add 10, what I did, and then 15, and then 20, 25, 30, 35, and so on. So you can't see anymore. So I'm not gonna add anything. But if I keep going, you see, this is like not anymore like a tree at all, right? So even if I add 5, we have one side of this tree that it's going to be only have one height of 1, and the other is going to have the height of, you know, very close to n, like number of the elements, right? So n minus 1 element are inside in the right side. That can happen if I go reverse, right? So these elements are almost sorted, and as I add them to the binary search tree, my binary search tree is no longer become balance, right? So the height of one side is going to be a lot more than the height on the other side. And so this way, when I'm trying to even search for an element or add a new element, almost going to take me or n minus 1 or n minus 2 comparison, which is going to be order of n. So it's no longer is going to give us the order of log n. So in the best case, this algorithm for search and for insert is acting as an order of log n, both in searching and in adding, insertion. So back to the slide. One more thing we would like to do before we start writing code is to understand that how we're going to traverse, right? Because we definitely want to be able to traverse. So that's our next important part for dealing with a binary search tree. So there are different ways to traversing a binary search tree or a tree in general, right? So these algorithms are very important. So here it's showing you as 4 different algorithms, but in overall, they are really 2 main type of traversing a tree. One is called depth first, and the other is going to be called breadth first, right? So DFS and BFS. Okay, so and these are the 2 main algorithms. The DFS has 3 different ways, and you're trying to depth first a tree or even later on a graph. You have 2 different ways to do that. You can do it in order, you can do it in pre-order, or you can do it in post-order. So they're all going to be considered as depth first, but just the order of the elements first, you're picking the middle or left or right, which one you're going to pick is going to be different from each other. And so you're traversing this or visiting each node on this tree in a different order. So if first go basically, we're going to first go over all of the depth first. So if I want a depth first a tree, and I want to use an in order, and it's clear from its name. If I do that, then that means that first I'm going to visit left subtree, and it's going to happen recursively. So I'm going to see all the left children's first, and then when I'm done with all the lefts, then I go to the current nodes, right, itself. So basically all the middle children's. And then if there's no more, middle children, then finally go to the rights. And then I'll go to all the way to all the rights. So since we do that, if we print, for example, all the elements out in order, from its name, you can tell that there's going to be print them out in a very sorted way, right? So from the small number all the way to the large number, because we first go to the left, and left's always going to be smaller, and then we'll go to middle, and then we'll go to the right, and right always going to be bigger. So we basically sorting this as we're traversing it. That's an in order. We also have post order, right? So post order is going to be that we first going to visit left again, and all the lefts, like recursively going to go left all the way to having no left anymore. And then we're going to go to right, and we're going to do all the rights, and then finally we're going to the middle ones or current nodes itself. So the first one was left, middle, right. This one is left, right, middle. And the next way is going to be called the pre-order. The pre-order is going to first do the middle element first, and then left and right. So middle, left, right. So this is going to help us to traversing our tree in the depth first. They're all going to go to the depth of each branch of the tree, either to the left or right or middles, and they're going to print the elements, right? So that's what they call them depth first. They're all three of them considered depth first.